So let's start the second lecture in Unit 6. It says, isn't it covalent? And so when we're looking at this, the learning goals that we have, we're going to identify the need for multiple bonds and distinguish between empirical and molecular formulas. So when we're looking at this, what we already know is that atoms can share electrons resulting in covalent bonds. And molecules are used in chemistry or moles are used in chemistry calculations. And then percent composition can be used to determine the amount of each atom. What we learned in the lab is that electrons can share multiple bonds, and that every shared pair of electrons results in a bond. So we're looking at covalent bonds. Those bonds can be separated by Lewis dot structures. So when we're forming diatomic fluorine, we see that those two are shared, and so it creates this bond. And we say that shared electrons are represented by a line. So once we see that these two electrons are sharing, we just represent that sharing by a bond or just a line. So multiple bonds. Some elements share more than one electron with a neighboring atom. Usual suspects, we're talking about carbon, nitrogen, oxygen. They can form multiple bonds, double and even triple bonds. And so when we're looking at these, the procedure for determining if it needs a more than one bond. So when we're looking at this, and when we look at something simple like fluorine, well, we have fluorine and fluorine. When they're bonded together, they have 7, and so therefore they just share 2 in the middle, and each one thinks that they have 8. So let's look at multiple bonds. So the first thing we do is, number 1, is we pick a central atom. So a central atom, and essentially for our class, a central atom is going to probably be the one that's just by itself. Carbon loves to be the central atom, so if we find a carbon, it's always going to be carbon. Hydrogen's never the central atom, it's always on the outside. And so what we want to do is, when we're working with it, we pick a central atom. And since we have carbon here, we're going to put carbon in the middle and then put the other ones around. And so all we do is we pick a central atom and then put everything else around that central atom. We count the total number of valence electrons. So oxygen, one of them has 6, the other one has 6, and carbon has 4. So 6 plus 6 is going to give us 12, plus 4 is going to give us a total amount of 16 electrons, valence electrons to work with. So after this, what we do is we connect the atoms with a single covalent bond and subtract 2 elements from the total number of electrons. So we make one single bond right here and one single bond right there. So we made 2 single bonds. So that represents 2 electrons, and that represents 2 electrons. So now we had 16 to work with. We subtract 4, and we get a total of 12 left. Okay, and then we have to look. If, it says on number 4, it says count the number of electrons required for every atom to satisfy the octet rule after taking into account the bonding electrons. So remember that this is 2, and that means that this oxygen thinks it has 2, this carbon thinks it has 2. This is 2, which again is the same on the other side. So when we're looking at this, this carbon has 1, 2, 3, 4 electrons around it. So to satisfy the octet rule, 8 minus 4, it needs 4 more. But this oxygen only has these 2 right here in that bond. So we go 8 minus 2 is 6. So each one needs 6. Each oxygen needs 6. So we need 6 plus 6 is going to give us 12. And plus 4 is going to give us not 18, but 16. And so it needs 16. Well, how many do we have left? 12. Well, that's not going to work. So what we do is, if the number of necessary electrons equals the number of valence electrons, fill them in. And so basically, if the number necessary, so what we have, equals the number available, we just fill them in. So if we had 16, we would just put all 16 of those dots around. But we don't have that. If there's an electron, add up a double bond, a second bond, and repeat step 5. So what we do is we have 12 available, and then only 16 need 16. So what we do is we make a double bond. Boom. And we make a double bond, and what happens is now, when we're looking at it, we've made that double bond, And we see that, well, this oxygen only needs 4 more, this carbon only needs 2, this oxygen needs 6. So 4, 2, and 6 will give us a total of 12. But in making this bond, we had 12. We made that bond, we subtracted 2. Now we were down to 10. Well, it still doesn't match up, so we just keep repeating it. Well, we keep going. And what we do is we go ahead and we make another double bond. And let's do it on the other side. So we'll make another double bond right here. And what we look is we see, hey, now this oxygen only needs 4. This oxygen only needs 4. This carbon has 8 now. It doesn't need any more. So now we have 8 total available left. How did we get to 8? Well, we made another bond, right? So we took our 10 minus our 2, which gave us 8. So we have 8 available now, and guess what? We only need 8. So all we do from here is we fill it in. So how many does this oxygen need? 4. So guess what we do? 1, 2, 3, 4. We put 4 around it. This oxygen needs 4. 1, 2, 3, 4. And guess what? It satisfies the octet rule. It looks like this, and that means that everybody has 8. Everybody satisfied the octet rule, and we're done. So let's look. It says determine the number of bonds between an atom, between the atoms below. They are shown in order of connectivity. So when we're looking at this, again, what we do is we start with how many valence electrons we have. Hydrogen brings 1, carbon brings 4, nitrogen brings 5, for a total of 10. So we get to work with 10. Well, first thing we do is make a bond. Bond. That took care of 2 right there, 2 right there, so a total of 4. Minus 4, we're down to 6. So we have 6 electrons left. Okay, how many does hydrogen need? Well, hydrogen follows the duet rule. It only needs 2. So guess what? Hydrogen's, it's fine, it's happy. This carbon, though, it needs 4 more. Carbon needs 4. In nitrogen, it needs, since it only has 2 right here, it needs 6 more. So 4 plus 6 is 10. Well, that didn't work. We only have 6 left. So let's make another bond. Bond. Subtract 2. We have 4 left. Well, this carbon, guess how many more it needs? It needs 2 more. This nitrogen needs 4 more, for a total of 6. Do we have 6? Nope. So make another bond. Boom. Subtract 2. And we have 2 left. Well, now this carbon needs 0. So the carbon needs no more electrons, and the nitrogen needs how many? 2. Well, how many do we have left? 2. Perfect. 1, 2. Now everything satisfies the octet rule, and we see that we have a single bond between carbon and hydrogen and a triple bond between carbon and nitrogen. The next one, it says draw the Lewis structure of nitrate. Don't forget the charge. So nitrate, what it is, nitrate is NO3 with a -1 charge. That means it has 1 more electron. So first thing we do is pick a central atom. Well, that's going to be the one by itself. Nitrogen, and then we put 3 oxygens. 1, 2, 3. Now we have to count up the number of valence electrons. Nitrogen has 5. Oxygen, which there's 3 of them, have 6 apiece. So 3 times 6 is 18. So 5 plus 18 is how many? 23. But remember, it has a negative charge, so it has 1 more electron. So 24. So we're working with 24 electrons. Next step, we bond. And so that took care of 2, 4, 6. So 24 minus 6 is 18. So how many more does, when we're looking at this, how many more does each oxygen need? Well, each oxygen needs 6 more. So we need 18 for them, plus nitrogen needs 2 more. So a total of how many? 20. Well, when we're looking at this, it needs 20 electrons. We only have 18, so guess what we got to do? Go ahead, make a double bond, and we double bond here. And now, subtract 2, now we have 16 left. So when we're looking at this, nitrogen needs how many? Well, 0. It has 8. If you look at it, it has 1, 2, 3, 4, 5, 6, 7, 8 with all its bonds. So nitrogen needs 0. This oxygen only needs 4. This other 2 oxygen needs 6, which is a total of 12 plus 4 is 16. Hey, that's exactly how much we have left, so let's go ahead and distribute those guys. This oxygen needs 4, so 1, 2, 3, 4. This oxygen needs 6, 1, 2, 3, 4, 5, 6. And this oxygen needs 6, 1, 2, 3, 4, 5, 6. Everybody's happy. And the way we represent the charge is we kind of put it in brackets and say, hey, we add an electron to that guy, so we put a negative out there. And our mastery level question says the compound CH2 cannot be formed by stable covalent bond. Explain why not and justify your answer using the clear method. So if we try to form this, carbon goes in the middle, hydrogen, hydrogen. We have 4 from carbon, 1 from each oxygen, so we have a total of 6. And now we bond. And that took care of 4. We only have 2 electrons left. So when we're looking at this, carbon needs 4 more, right? So it needs 4 more. We only have 2 left. Well, we can do a double bond, but guess what? That took care of 2. Now we have 0 electrons left, and carbon still doesn't have an octet. Well, what we could say is that it's impossible, and this double bond between that hydrogen, not happening because that's a duet rule. So what we would say is we would say that this cannot happen because hydrogen cannot form a double bond, and we don't have enough for carbon to complete an octet. Now, jumping into molecular formula. Now, molecular formula, now that we know how to write the structure of covalent compounds, we know kind of how to put their Lewis structures around how they bond, and we know their names. Let's talk about molecular formula. Now, molecular formula represents the number and type, so the number and type of atoms. It doesn't show the connectivity, so how they connect. So if we're looking at this could be the molecular formula. We have C4, H10, and O. So we have 4 carbons, 10 hydrogens, and 1 oxygen. That's a molecular formula. Now, an empirical formula, on the other hand, empirical formula represents the lowest whole number ratio between different types of atoms. So if our molecular formula was C4H10 we can reduce 4, 10, and 2 by 2 and reduce it down to 2, 5, and 1. And so the empirical formula is just the reduced formula of the molecular formula. And it's shown by percent composition. So how we find the empirical formula? We show that by percent composition. What is percent composition? Well, percent composition is percent of mass of oxygen. So, or percent of mass of each element. In this case, we're looking at oxygen. So when we're looking at percent composition, well, how much of this molecule is oxygen by mass? So when we look at this, all we do is we take the number of each and the mass of each. So a mass of carbon is 12, a mass of hydrogen is 1, mass of 1 oxygen is 16. And what we do is we multiply them by how many are in the formula. So we have our carbon, which we have 4. Hydrogen, we have 10. Oxygen, we have 6. We get their masses, their total masses. So in this formula, the mass of carbon is 48. The mass of hydrogen is 10. The mass of oxygen is 16. For a total mass of the whole thing, which is the molar mass, of 154. So the percent composition by mass is just we take, well, if carbon has a mass of 48, but the whole thing is 154, it has 31.17% of that is carbon. Hydrogen, if it has a mass of 10 and the whole thing is 154, it has 6.49% mass of hydrogen. And then oxygen is 96 divided by 154, a mass of 62.34%, which adds up to 100. So percent composition is just showing the mass of that particular substance. So in looking at this, it says the formula shown below is given to a chemistry student. Determine if the formula could be an empirical formula, molecular formula, both, or neither. Then determine the percent composition of hydrogen. So when we're looking at this, we know that this very first one, that it's C3H12O2. So we know that It can't be reduced anymore. So guess what? It's the empirical formula, because we can't reduce a 2, a 12, and a 3 any more than what they are. So we know that it's empirical formula. Now it could be the molecular formula. If this is actually what it is, and it's actually the substance that they have, well, then it's the molecular formula as well. So molecular formulas can be empirical formulas, but empirical formulas aren't always molecular formulas. So next thing we want to do is we want to determine the percent composition of hydrogen. So when we're looking at this, what we do is we set it up where we have carbon, we have 12 grams, because that's what's on the periodic table. Hydrogen is 1 gram, oxygen is 16. Multiply it by how many we have. We have 3 carbons, we have 12 hydrogens, and we have 2 oxygens, for a total of 36, 12, 32. And 36 plus 12 plus 32 is going to give us 80. So we take this, and if we want to determine the percent composition of hydrogen, we take the part of hydrogen, which is 12. The whole thing weighs 80, divide it by 80, and then what we'll do to find the percent, multiply it by 100. So 12 divided by 80 is going to give us right around, multiplied by 100, would give us 15%. So 15% of the mass of that molecule is going to be hydrogen. Next question, it says, what is the percent composition of carbon in octane? So this is what goes into your cars, and this is what a motorized vehicle is made of. So when we're looking at this, we have carbon and we have hydrogen. That's all we have. We have 12 for carbon, that's its mass. Hydrogen's 1. We have 8 carbons. We have 18 hydrogens. We multiply these guys out, and our carbons are going to give us right around 96, and our hydrogen is going to give us 18. For a total of, it gives us a total mass of 114, right around there. And so it wants to know the percent composition of carbon. Okay, so when we're looking at this, we take 96 all divided by 114, and that will give us right around an 84% of that will be carbon. And looking at our next one, it says thiamine is one of 4 nucleotides that stores genetic information in the deoxyribose nucleic acid, which that's DNA. And it says, what is the percent composition of each element in thiamine? So when we're looking at this, very big formula, and we got a lot of things in here. So let's go ahead and try to break it up. We have carbon, we have hydrogen, we have chlorine, we have nitrogen and oxygen, and we have sulfur. We write out their masses. Carbon's 12, hydrogen's 1, chlorine's 35.45, nitrogen is 14.01, oxygen is going to be right down around 16.00, and sulfur is 32.06. And this is actually 12.01 and 0.01 for hydrogen. We multiply by each one of what we have. So carbon, we have 12, hydrogen, we have 17, chlorine, we just have 1. Nitrogen, we have 4. Oxygens, we just have 1. Sulfur, we just have 1. We multiply those guys out. So we'll do the ones, 35.45, that was easy. 16.00, 32.06, and then we have our 17.17, and then we have our 144.12, and then we have down here with our nitrogen we have 56.03. We add all of these up and we'll get a total of 300, right around 300.81, and then we just divide each one of these by 300.81, which will get about 47.91% carbon, 17.13% hydrogen. We'll get 35.45 percent chlorine, we'll get right around 5.32 for oxygen, 10.66 for sulfur. And so we'll get right around all those percentages for each one of those guys. Now, when we're looking at determining molecular formula, now that we know what they are, we know what covalent compounds are and everything else, we want to determine molecular formulas. So we were going to take, now that we know what percent composition is, we can calculate percent composition, we want to in turn show how percent composition tells us the molecular formula. And there's a lot of steps to it, so try to stick with it. The first one is determine the molecular formula. We convert the percentages to mass, assuming there's 100 grams. Pretty simple. Take your percentages, put grams by it, done. First step, done. Next thing, we take the grams that we just turned the percent into grams, and what we do is we divide using their atomic mass or their molar mass. So we convert from grams to moles. So divide carbon by 12, hydrogen by 1, and then oxygen by 16. And this gives us the moles of each one. And then all we do is we take those moles and we divide by the smallest mole. So if we're looking at this, the smallest mole will be carbon, 2.5975. And we divide each one of these guys by 2.5975. And you can see that on the next one. And what we get is we get something essentially that is 2.5, really close to 2.5, and something that's essentially 1.5. Now, what we can't do is we can't make this 1, 2.5, and so on. So what we do is we go ahead and we know that if we multiply and just start at 2. So we go, okay, these guys are 1, 2.5, and 1.5. Multiply each one by 2, we get 2, 5, and 3. Well, those are whole numbers. That can work. We can't have non-whole numbers. We have to have integers in our equation. So we multiply them out by 2, and we get 2, 5, and 3. So 2 carbons, 5 hydrogens, 3 oxygens. And that will give us our formula. And so if these guys right here were 2, 5, and 3, we would stop there. We wouldn't have to multiply. But since they weren't whole numbers, go ahead and multiply. Now, if we look at it, this is a molecular formula. This is an empirical formula. They both have the same percent composition, because when we're doing those steps, that just tells us the percent composition, just tells us the empirical formula. It doesn't always tell us the molecular formula. So what we do, empirical formulas are the simplest whole number ratio of atoms in a molecule. And percent composition can only tell us the empirical formula, not the molecular. So what they use is they use a device called a mass spectrometer. And what a mass spectrometer is, a mass spectrometer, it measures the mass of the molecule. It gives us the mass, and just by looking at the numbers over here, it basically gives us the mass of the molecule. And what this does is it's going to give us a multiplier. So here's the mass of the molecule. Will you have to read one of these or actually do one of those? No. But basically what they do is they stick the sample in a machine, and the machine tells us what the molecular mass is. So let's go ahead and use that information and do an example. It says the student is attempting to ascertain the identity of a sample based on the information given below. We have our percent composition. Let's go ahead and figure it out. So the first step is we change it to grams. Way to go, grams, 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 grams. Way to go, awesome. Next thing what we do is we take this and we go ahead and we divide by the atomic mass. So when we go ahead and we divide by the atomic mass, we divide by sodium on the periodic table is 22.99. Hydrogen is 1.01. Phosphorus is 30.97, and oxygen is right around 16.00. This gives us the moles. So when we're looking at this, it gives us essentially something that is 1.4, 1.4, 0.7, and 2.8. So what is the smallest value out of all of those guys? Well, out of all of those guys, smallest value is, didn't want to move it, smallest value is going to be 0.7. So we just take each one of these and divide by 0.7. And what we see is we get 2 for sodium, we get 2 for our hydrogen, we get 1 for our phosphorus, and we get 4 for our oxygen. And so our formula is sodium, which is Na, and we have 2 of them, hydrogen, which is 2 of them, phosphorus, which is 1 of them, and oxygen, which is 4 of them. And we would have this for our equation. Looking at our next one, it says a sample is combusted, resulting in the data below as shown. So if we're looking, we got our percent composition of carbon, hydrogen, and oxygen. Further analysis showed that the sample has 6 carbons. What is the molecular formula of the sample? So when we're looking at this, we're going to do the same steps that we have been doing. We got a percent composition. Let's go ahead and work this out. So carbon, we would go ahead and we divide that by 12.01. Hydrogen 1.01, oxygen 16.00, and that will give us our moles. Our moles are going to be 3.33. Hydrogen is going to be right around 6.67, and our oxygen is going to be right around 3.33. If we look at this, the smallest number is 3.33, so we divide each one by 3.33. And we see that we will get a 1, a 2, and a 1. So our empirical formula is CH2O. We have that. But it says that if it put it through the mass spec, it has 6 carbons. So for that carbon to have 6, we'd have to multiply that 1 by how many? 6. So we get C6. H, if we multiplied by 6, we would get 12, and then O, 6. Well, if we look at this, we see that that is glucose.